Hi everybody, and welcome to this talk on Project Leyden. Capturing lightning in a bottle sounds exciting. So is it possible to reduce the startup time of your application today and cut it into half? And is it possible in the future to maybe reduce the startup time with an order of magnitude? I'm Per, and I work in the core Java library team at Oracle. So let's take a step back and look at some things that's going on within the Java community. So we have Project Amber, has delivered a lot of language features like sealed classes and records, pattern matching, and a lot of good stuff. I think we're now up to 23 apps, which is very good. We have a new product called Babylon, which is about extending Java's reach so we can express our logic and code, and then we can reflect on the code and maybe translate it to SQL or machine learning or graphic card instructions like kernels and stuff like that. We have Project Leyden, which I'm not going to spoil all the fun at this stage, so I'm going to leave it there. We have Product Lilliput, which is about downsizing Java objects headers from 128 to 64 bits or even lower. And why is that important? That's just 64 less bits. But if you have billions of objects, that will really make an impact, not only in terms of storage, but in terms of performance, because your locality will improve. Project Loom has just delivered in Java 21 with lightweight threads, so you can now have 100% utilization of your CPU and not only get constraints by your server's memory. We have Product Panama, which actually is going to be final, at least part of it, in Java 22 and the next RC. The first release candidate is in 2 days. So that's a big thing for us. We'll be working hard with that. So the native function and memory API is the first drop. And now you can link or bind to native methods directly in Java, so you don't have to use JNI and peculiar libraries to do that. There is also another part that allows you to work with memory, like this is the byte buffer plus kind of interface, much faster and much more expressive than a byte buffer. Then we have vector support, which has previewed for a record 7th time. And the reason for that is that we're waiting for Valhalla because we need to synchronize the API towards value classes. And the slogan for Valhalla is code like a class that works like an int. So basically you can have a list of integer, but under the hood it can be flattened out and really use real integers. So you have a point with x and y that will all be flattened out in memory. And again, that will improve memory usage and locality. We also have this ZGC, a load scalable low latency garbage collector that allows you to have heaps of in the terabytes, like 8 terabytes or 16 terabytes or so. So that was in alphabetic order. This is kind of an iceberg order. OpenJDK, we know what that is. Amber, we understand the new features. But Leyden, what is that? And hopefully I'll be able to sort out some of the issues around that. So Project Leyden is about improving startup, warm-up, and footprint on Java applications. And before we go into that, we might take a step back and think about what is startup. And startup is the time it takes to get the first useful work. So if you have a hello world, it's the time before you start your application and measure to when you see hello world on your terminal. And in a more realistic case, it's when you start your web server and then you actually are able to serve the first incoming request. Warm-up, on the other hand, is the time it takes before the application to reach its peak performance. We all know that Java is slow in the beginning, or relatively slow, but at the end it's really fast. But it takes a while, and we will come back to why that is the case. Footprint is another kind of property that I won't talk about so much today because we haven't worked so much with it in this project, but it's more a broader definition. Can be the amount of footprint it takes to actually deploy your jar file or the amount of memory your application is using on the server. So maybe we should do a raise of hands. Is startup something that you're concerned with today? Okay, I see a lot of hands. What about warm-up? Slightly less. And footprint? Okay, so you're interested. You are in the right session then, obviously. So they all are influenced by work done with by the application, but also work that's done on behalf of the application, for example, loading and compiling classes. And the startup and warmup are an issue for Java application because Java is highly dynamic. We will come back to that too. But wait, when I tweeted about this last week, I got some answers. And someone was saying, well, isn't native image the way to do? Isn't it a solved problem? Well, it might be if you are fine with living in a prison, basically, because you are not able to, redefine your classes. You can't put a new UR on the class path. And you're also accepting that maybe my application isn't going to run that fast as it would otherwise. So it's kind of a trade-off. But it's a good trade-off in certain application. That's okay. But wait again. Here is another, I think, clever comment. So if we run a sample Spring Boot application, it takes 4 seconds, but if we use OpenJDK Crack, it will take 40 milliseconds. So that's 2 orders of magnitudes. So isn't that great? Well, this brings me to this thing. Does anybody know what it is? I know what it is. No one. Oh, when I was a teenager, there may be one there. When I was a teenager, I kind of coded games. That's how I learned how to code with computers. And I love coding games, but I also like to play games. And as I was a teenager, my budget was, a bit limited. So another, thing we did was to crack games so we can copy them. And I should note that at this time in Sweden, that was perfectly legal. But I think it's forgotten anyway. And what is this? Well, this is something you can put into the expansion slot of your C64 computer. And if you look at it, we see that this is a 74LS30, that's a NAND. And they have other chips here, which are sanded away, so you couldn't copy it. But of course, we could copy it anyhow. But I think those up there are just the O4s, so they were fed into the NAND grid and create a chip select signal for this static RAM, which is the big one there. And there's also a switch up there. So this thing has 3 modes. So when you plug it in, you have first a bootstrap mode. So you run a program which will upload some machine code on the static RAM chip here. And then there's a second mode, which is the stealth mode. So you put in the stealth mode, you loaded your games, and hopefully it didn't detect that you have put this in. And you loaded everything, it passed the copy protection stuff, and then you switch the switch again, and then you come into the crack mode. And what it did was it generated a non-maskable interrupt, and the jump vector was set to the machine code that was uploaded in this chip here. And of course that took a copy of all the RAM, all the video registers, CPU register, everything, and created an image. And then there was a bootloader that loaded everything, unpacked it, set the stack pointer and executed return from interrupt, and bang, you were up there in your game, just as it was before you switched. And that spoiled all the fun because there were all the pecking order in the crack community was gone because it was so easy to use this one. But this guy is 40 years old. So this shows that some things aren't that new as you might think. So this cracker leads to crack, which is the software version of this one. So in the same way as this only works for the C64, crack only works for Linux. You can't run it on an Apple, for example, or a Windows machine. So that's one problem. And another thing was that eventually there was this arms race. So the guys who were doing like games, they figured out that they can store data in some obscure timer or some video registers that wasn't really copied. And that's the same thing, a problem with the crack. So if you have a file open or you have a socket open, then you have to install a special handler for that. So that when you go back from the checkpoints, you have to reestablish your file or you have to reopen your socket. So I think Leyden has a broader kind of aim than these two. There's nothing wrong with the solutions that I mentioned, but they have a more narrow target group. So the purpose with Leyden is to shift computation temporarily. I mean, not temporary, but in the temporal domain. So we can shift things earlier or shift things later in time. And we are going to introduce constraints to Java's dynamism to enable more and better shifting. And we're going to do that selectively. So you can select what kind of constraints would I like to have. And also compatibly preserving program meaning. So we don't want to have extra APIs or something like that to be able to use this feature. So I would like to illustrate this with this mixer board, because I like music too. So maybe the sliders here can illustrate like your 12 different applications, and maybe the first application up here. I'm willing to concede a lot of dynamism. Maybe I would put the slider all the way up so I can accept this kind of closed world. And then maybe as an emerging property, Leyden will provide you with a static image. But for the other ones on the left-hand side there, I don't want to concede to anything. Then maybe Leyden can give you a little bit better performance, but not as so much. And it's important that you as a programmer should be in charge of what's doing this, just as a DJ is in the music domain. So Java is dynamic, but we thought that Java was a static language. Isn't Java statically typed? And then Python is like dynamically typed. Well, that's true. If we think that static means compile time and dynamic means at runtime, is Java statically typed or dynamically typed? And the answer is yes, it's both. So we have a static type system, of course. When we compile, we can't assign a string to an int, for example. But we also have a dynamic type system enforced at runtime. Because if we have an array of ints, we can cast it to an array of objects, and then we can try to assign an element in that to a string. But of course, we cannot allow that because that will kind of create heap pollution. So we will get this kind of array store exception at the base there. So the answer is it's both static and dynamically typed. So this kind of gives a certain dissonance. And when we smell a dissonance, it's always good to go to the dictionary and see what do we mean as static and dynamic. So we have statics like this: remain stationary, no inertia, no movement, doesn't change. And dynamic, on the other hand, is the opposite: moving around, highly energetic, a lot of inertia, it's changing. So maybe it's better to talk about what is changing and what is not changing. And one aspect, of course, is what is changing. And in the context of language, you often think about type checking, but there's so much more to think about. For example, in Java, we have dynamic typing, which we just talked about. We have dynamic class loading and verification, dynamic class redefinition. We have dynamic compilation, jitting. Jitting is when you're compiling code after you started to run, so that's short for just-in-time compilation. We have dynamic recompilation, so maybe we compiled under certain premises or presumptions, but maybe those presumptions don't hold anymore. And then we have the option to de-optimize. So we said, we tried to do this, it worked for a while, but then we discover it didn't work, so then we can go back again. We have dynamic linkage and access control. So the first time we call a method, we have to establish that we actually can call this. Maybe we are on a module and that method isn't visible. And that is something that's only taking place once. And then we cache that information. And we can also introspect instance of. And we have dynamic dispatch where we select which kind of variant of implementation in an interface do we do, like VTabs and things like that. So another distinction is over what period is something changing or not changing. So if we look at this small code line up here, it says static final long and some variable name, system current time milliseconds. Is this static? Well, it says static. It says there on the text. So it's static in some sense. But the initializer runs at runtime. And that sounds pretty dynamic. But then again, the value is only held constant for a certain lifetime of this. For example, when the class initialized, or for example, until the JVM exits. So this is kind of static again. But the lifetime doesn't coincide with compile time and runtime. So this is kind of another domain, for and when is it constant. So this kind of shows things that are board dynamic but treated constant by the JVM. And the JVM is very good at optimizing things like that. So Java has really the answer, choose one, lose one. So it is kind of yin and yang relation between static and final. There is more to the born dynamic thing. We have static field installation, we have class loading, and there are in fact many other optimizations that they do routinely for us to provide good performance. One example of that is class hierarchy speculative optimization. So suppose you have one interface and you only have one implementation of that particular interface. Then you know that I'm going to call this method because this is the only implementation of that interface that I have. But then maybe sometimes after you put a new jar on the class path, and suddenly there is another implementation there. But that's not a problem because it's the same JVM that loads the class, so it will see that, okay, stop here, I'm gonna, evict this from the code cache, the compiled code, and say that, well, you had to go back again and work with this new assumption that there are two implementations. And then eventually it will get optimized again. So we take this kind of optimistic approach, but we are allowed to fail. So what happens during startup? Well, if we look at the things that your code does, it's like it can read configuration files, scanning annotations, opening sockets, creating loggers. These are things that we see in almost any web application. And that results in class being loaded from disk, class file validation, running initializers, interpreting code, gathering profile information, and all this call site linkage, which I talked about before. I should mention profile gathering is something that's being done continuously by the JVM. So it will gather statistics of how your code runs. And then we can use that statistic when we eventually do a more performant compilation. I will come back to that. During warmup, our own code sometimes will populate caches that are not populated from the beginning. And the JVM will do, compilation, which we mentioned here several times. And compilation is done in several tiers. So we have the C1, which is the slower one, like in this room, C1. And maybe the guys are talking faster in C2 here, I don't know. And also Graal. So why do we do this? Are we like crazy doing all the things all the time? Why is this the case? Yeah, because it provides Java with a lot of expressiveness. So there's a lot of libraries out there relying on reflection, lazy loading, and all that stuff that we really don't want to refrain from using. And the thing is that it's actually good to defer compilation as long as possible because we, as opposed to C, for example, we can see exactly what kind of hardware we have. What kind of CPU stepping do we have? How much memory do I have? How many CPUs? How are the cores connected? There are so many things we can harvest. We have the profiling data too. So we know not only what we should do, but how it's been done from a statistic point of view. So maybe we have a method that's being called by some reference, and we have entered that method 30,000 times and never have a null as an argument. And then I think it's safe to say that we can compile code that optimistically thinks that this will never be null. And we can compile something that doesn't check it, but then generate some kind of trapping mechanisms so that if it is null, we will generate the trap and then we will de-optimize and eventually go back again. So I think this is the reason why Java sometimes are so much faster than C. Okay, so that is good. But there is also a cost. So the cost we are paying is slower startup and slower warmup. But this is still good for many applications. So suppose you have, maybe you have some risk management application running and you start it and it will run for half a year or a year or so. Then this is a great trade-off because you will not even start up your programs more than 2 times a year. So that's okay. But for other application, it's not that good, especially if you have something in the cloud and you want to dynamically scale up your capacity, then it's important that your application will start and is ready to take on work. So here we see a kind of an idealist picture of an application. These are just made up figures. And the green line represents something ideal. So the first time we are running, it takes some little bit more time because we do things internally up, maybe populating some caches. But then eventually we will reach a good performance here. But typically we are seeing the yellow line here. So we will have a very long start time, and then we have some deficit towards the ideal case, but eventually the curves will narrow each other. So I think the integral under here is the kind of things we are paying for startup, and that's usually measured in milliseconds. And time to, JIT activity warm-ups is often measured in seconds. It should be noted that it's not necessarily related to the time, it's more related to how our application is used. So if we only have like one request per second, it will take longer, of course, whereas in another application we have a million requests per second. That will be different time, obviously. So what we want to do is to kind of push down this yellow initial there, and also push down this kind of horizontal curve, the yellow one, and try to eliminate this as much as possible. So how can we do that? Well, we have to shift work off the critical path. So we can shift work in earlier in time, such as by employing laziness, or we can shift work earlier in time and do things at build time rather than on runtime. And this applies both to actual work being done in our application and things that are done on behalf of the application. And we already do this today in a number of things, in a number of ways, which I have spoken about before. So here are some other examples. Compile tally constant folding is like when I have an expression and I know I only have constant here. So I can, if I have 1 plus 2, I know it's 3. So I don't have to calculate that at runtime. Garbage collection is actually something that you postponed. It's a moving things later. So when something is not phantom reachable anymore, one example could be that we would free it immediately, but that will be very costly because our application has to stop and we have to mark it as free. So instead we just leave it there and leave it to the garbage collector to pick it up later. We have class loading and initialization, which make things later in time. There are also some things you can do today. We can compile ahead of time, like a native image, which is spoken about before. And there is also something called class data sharing archives. So we can, pre-dig class data, save it to a file, and when we start up, we can just read the file rather than just parsing everything. And that will improve startup time. And this is fair game, as long as we don't change program meaning. If we go a bit lower, we can look at the Java memory model, which is also kind of shifting computation in time. So the semantics is that if I am within a thread, it should be as if serial semantics. So if I want to compute a variable A and variable B, and then use variable A, the compiler is free to shift so that I compile B before A if there is no coupling. And then I have A kind of recent and I can start working with it. So that's perfectly fine. Another thing is that threads have different views of data. So if I update something in one thread, it might not even be seen in another thread, or it might be partially seen, or it might completely be seen. And therefore, we have something called happens before. So everything in a single thread, by definition, if there is an action X and there is a subsequent action Y, then X happens before Y in that particular thread. But that's not true for inter-thread communication. So you have to insert memory barriers, for example, to ensure that X happens before Y. And this is a performance issue because the memory subsystem can be more efficient when you don't have to see through everything. Other things we can do here is to remove redundant synchronization. So if an object is not observable from another thread, why even synchronize on it? And we can go deep, 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 like really deep under the iceberg. And here we have hardware level. So we have out-of-order execution. We have speculative branching. SIMD is like you can execute several instructions at the same time in parallel. We have CPU caches. So if you write something to main memory, You might just write to the cache, and it will never be written to memory because you might update it before it being flushed to main memory. And that also saves a lot of resources and increases performance. And there are many more things that the hardware does for us in terms of shifting. And Leyden will expand on this kind of theme of shifting things back and forth. So I just checked the time here. Well, it looks good. So you can do some shifting that requires no specification changes at all. For example, we can expand lambdas to ordinary bytecode at build time. You might know that if you have a lambda, there is something called a lambda factory that will kind of create the bytecode that's needed to implement the lambda, and that takes time. We can speculatively compile code ahead of time, and we will see how that is being done later on. Other things we can do with require specification changes is that we can eliminate dead code. So maybe we are really sure that we'll never reflect on some parts of the code, and then we can just strip it away. We are also looking to and exploring some additional things, like a new keyword in Java called lazy. So we can say that we have lazy static final foo, and then there is a lambda. So this variable here, the static variable, will be evaluated the first time we access it. And then this lambda being invoked, and the result will be eternalized into this variable here. Another thing which I have been working with actually together with Maurizio is something called computed constants. Actually, we have a draft YEP of this, and we might see it in any of the upcoming Java versions that are coming. And it's about if you have a variable that is final, you must initialize it before the constructor returns. But with computed constant, we decouple this kind of necessity. So you can have something final, but you can compute it much later, maybe in a completely different code path in your code. And that provides a lot of benefits. So we are leveraging something called @stable, which is an internal annotation that the JDK can optimize. And it's only usable for classes that are loading by the boot class loader. That is the JDK itself. But computed constant of many things provides a kind of wrapper around stable. So here is an example of how you can create a logger. So instead of having a private static final logger, you have a private static computed constant of logger. And then you say, I would like to have a computed constant of, and then you provide a lambda. So it's guaranteed that this lambda is invoked only once and before the get method. Note that I didn't say when the get method was invoked. So it's guaranteed it's invoked before the get method, the first get method returns. So it might never be invoked, for example, when you're calling it, or it might be evaluated under certain conditions before you invoke this one. And you will get exactly the same performance as you had declared something statically and computed it dynamically. So it looks like a library, but it leverages some JVM things. And it also provides benefits for both static and instance variables. So it can be used to replace the class holder idiom when you have a local small class that holds some variable. And it can also replace the double-checked locking idiom when we have synchronization around. And actually, it's faster than a double-checked locking too, as an extra benefit. So it will be interesting to see how people is using this. Just a second. So here is another more advanced example. So you can not only have a single instance, but you can also have collections of computed constants. So here we have a list of computed constants of type integer. And then we have the usual computer science example of Fibonacci. So you said that you have a Fibonacci buffer or cache of a certain upper bound. And I said my list is a computed constants of this many elements. And here is the lambda or the int function that I'm going to invoke when I'm accessing each and every element. So for example, if I go in here and access element 5, I will go through here and n is certainly higher or equal than 2. So I will kind of access list get n-4, which is the fourth element. And the fourth element representation of a computer constant doesn't exist. So it will create a computer constant. And then I will get the value of the computer constant, but it has no value. So it will go and invoke this lambda, and it will call recursively number and so on. So this will turn the kind of what you call exponential order exponential to an order n in this case. So when you go on the right-hand side, the get n-2 will already be computed. So that's interesting. And maybe we'll have also maps and other constructs that are kind of computer constants. Okay, so maybe we don't want to live in this closed world, or maybe we do want to make some concession, but somewhere in between. So some of the things we're exploring is maybe class X won't change, or I can live in a closed world, or no class definition of module M. So there's a lot of different kind of constraints we are looking at here. So who knows what this is going to lead to. It's still early days. So this brings us to condensers. So condenser is a new tool of Leyden that will be introduced in the build chain. And a condenser is something that will perform some kind of action in your code and shifting things earlier in time. So it will transform some kind of image and add things. So it potentially will create new code ahead of time compiled methods, maybe new data, serialized heap objects, new metadata, and then even maybe introduce new constraints while it's running. So this is the reason why it's called Leyden, because Leyden is a capacitor or a condenser. So that's one thing I wondered when I read about Leyden the first time. So condensers, they are meaning preserving, so they need to preserve program meaning. You can't have something that doesn't work, of course, because that's cheating. Condensers are composable, so you can run one composer, then you can run another composer, and maybe you can run the same composer again. So this kind of leads to the same problem or opportunity that compilers have, where you can go through optimization several times and create an even better image every time you go around in the circle. And condensers are selectable, so maybe they will get automatically selectable what you concede, or maybe you will be able to compose them by yourself. And if you're, for example, debugging, you might not care so much about doing any condensers because you just want to see how it looks like. But then again, if you're maybe in final stage of providing your production code, you might want to run a bunch of condensers to really improve performance. So, what can you do today? How many of you are using AppCDS? One. You're missing out on something real big here. I think we should spend some time here then. So CDS is something that was added very early in the JDK, and especially when we came to Java 8, we had a lot of lambdas, so we would like to have some additional information available already at startup. And in JDK 10, we enable also applications classes to participate in class data sharing. And basically, you will then have the opportunity to take a snapshot of your classes and store them in the CDS, so you can start up much faster. And I think also the objective for Leyden is to expand around CDS and make it more general, so we can create profile data and store them there, compile code, and even more metadata that we can put into the CDS. So it uses an archive file, and actually it's memory map when you start up. So it's about 500 times faster than generating all the classes, and you just map in the file, and there you have all the data you need. As the last one said, most people don't use AppCDS today, and I think we established that by the raise of hands. So this is how you do. You have a number of XXX commands. You dump loaded class file list, and you can run several times. You get a text file, and you can merge them together using some simple tool. And then you can run and dump all the code or all the class information down to the CDS archive. And then you can start up with another flag and use that custom CDS image that you have. So if we look at the performance here, you can see that without any CDS whatsoever, this kind of exemplary Java-C compiling took 300 milliseconds. And with the default CDS, it's 250. And with app CDS, it's almost 150 milliseconds. And I think this answers my first question that I had in the beginning. Can you slice half the starting time of your application today? And the answer is almost. This is 40%, but maybe in your application you can do 50%. Why don't you go home and try it out? And I think it's kind of a tedious process to run all these XXX, or not XXX, that's something else, but all the XX things here, and maybe we'll package them as a condenser. So you don't have to do this. This is just one condenser. So you run all the stuff, and all the flags will be handled automatically, and then you do a test run, and then it will be stored for you. So this is something called a training run, but the training run can do more. It can actually, run an integration test or against data that you have in your production system, and then it can gather all these profiling things that are there, and it can store them in the CDS record, and then you can just boot up with all that statistics and maybe compile much earlier. Or maybe you can even just slot in the compiled code directly and put it in the code cache from the beginning, and thereby not only start faster, but get performance much faster. So that sounds like a good idea. So we've done some experiments with this, and how far can we come with this kind of concepts? So before we go there, I want to talk about a little bit more about compilation. So I made this kind of very simplified image. So when we start, everything begins with interpreted mode. We will read each and every byte code, we will mutate memory, and we will go around like that. And that, of course, isn't that great in terms of performance. But it is great in the sense that we are gathering statistic and profile. We have full profiling at this stage, and that's good for the future. Then relatively soon, we will kind of elevate to the higher tiers, T2 and T3. I won't talk about T1 because it's kind of an obscure thing. And when we reach T3, we also have a full gathering of profiling information, and it's very quick it's a quick compiler, but it's not that efficient in terms of performance. And when we have gathered enough information, usually when we have called the method like 30,000 times, we have enough of profile data. So then we can go to tier 4, which is a C2 or Graal kind of compiler. And once we are there, we have great performance, but we don't do so much profiling anymore. And then we can de-optimize, which I talked about before. If we have some kind of presumption that doesn't hold, the JVM will detect that, and we will de-optimize, and we will go back to the beginning, and we will do new profiling information, and then we will kind of go on until we reach a kind of steady state. And that's what's been said on all these slides. So I will just go to the next slide. And this is just purely speculative. So it's okay to speculate and make the wrong assumptions. It doesn't matter so much. Okay, it will cost you some time or resources, but in terms of validity of your code, it doesn't matter so much. Okay. So we can extend the CDS, and we can gather information on all the tiers. We can compile and gather things that we have compiled in all the tiers 1 to 4. We can store class object, not only metadata, but mirrors of classes in C. We can resolve constant pool, references, classes and field, resolve all the invoked dynamic linkage things we talked about before. We can pre-initialize enum and hidden classes, and maybe we can do even some more. Yeah, I talked about this too, and this one too. So here is a case study. What happens if we are using all these prototyping things we have done? So the yellow one is a baseline. I think it's Java 22. It should be noted that these figures are a few months older, so it's a bit better today actually. But you will see the big picture. So the baseline is like 600 milliseconds in this case. But with Leyden, all the optimization I talked about, without consenting any dynamism in Java, we can slash the startup time in 2 and also improve on warmup, as you can see. So we have startup improvement here, and we have warmup improvements here. And that's great. So it's a little bit closer to the ideal situation. So if we look at this, we can shift information early in time via CDS. We didn't introduce any new constraints, but there was no magic. All the things I talked about before contributed to these improvements. There are some kind of, which I don't have time to mention right now, but some problems that we are working with, or not problems, but optimization opportunities, I would say. It's a better word. So here is another case study. We are running some spec JVM XML parsing. And in this case, we actually achieved 8 times startup improvement. And it's very good. And I think it's like, but we didn't achieve any warm-up. So I think this is another case. It's another workload. So I think it's one of those situations when you really have to try your own application and see how much does this give for me. So for some application, startup is the only important thing. If you have an interactive application, for example, it doesn't matter if it's fast. The most important thing is that I get a prompt and I can do something. Here is an interesting one. This is called Spring Boot Pet Clinic, and Pet Clinic is kind of a Hello World plus for Spring. And to the left-hand side, we have the baseline JDK 22. And then the orange one is like we took the jar and unpacked it. This is something people regularly do when they deploy things in order to improve startup time. And the blue one is with static CDS, and the black is with dynamic CDS, which I talked about just recently. And then, of course, Spring has its own trickery and hackery-pockery that it does, and it wires all the annotations and binding all the methods together with this kind of own thing it does, and that improves performance also. So this slide says 4.1 startup, but I think that's a bit unfair because it includes all the other actions taken here. So I won't claim that figure, but it's still a good improvement. Yeah, so there are more things we can do. So I think the Spring scanner, or what you call it, could actually be one of, in the future, could be a condenser. So the Spring magic thing could be shipped as a condenser in the future. I think we talked about this. So this is time-shifting speculative optimization works. So there was a significant gain with this. We have full compatibility, no new constraints, no changing of the program model, no changes to specification, and it retained all Java's natural dynamism. So we haven't started to kind of pull up the potentiometer in the mixer board yet. This is just, we don't want to concede anything. So I think that's good. And we are working with this. It's still early days. And we are looking forward to maybe come up with the first JEP, which might be an expansion of the CDS archives to be able to hold all this kind of extra information we want to put in there. More to come. Introduce condenser. That will be a next step. We have a prototype up for condensers, which is a kind of an immutable model, and that is composable. We're going to look at what kind of more things, what kind of more constraints of dynamism makes sense, and a final way to bring in the shiftability into the program model. So we're just getting started here. So great. So with that, I will open up for questions. Well, I know this is Sweden, but it's allowed to raise your hand. Yes? We didn't have any formal name, so we were not the top tier. So we were a little bit down in the pecking order, I'm afraid. Yeah. Oh, sorry. Yeah. Yeah. So the question is, I think, what steps are included to put the potentiometer at the top? What do we sacrifice? Is that correct? So that is something we are working on. I think eventually at the top it's a closed world assumption. So we will have no reflection, no addition of code, no dynamic proxies, maybe other restrictions there too. Restrictions on method handles or var handles, things like that. So that's a quite severe restriction, I would say. And that's okay in many applications, but maybe in the vast majority, it's not okay. So it's still up to you where you will have the slider. Okay, thank you very much, and I will stay here for additional questions.